Well, thank you very much for having me. It's always a pleasure to come to the Oyster. Maybe at one point I will make it in person, but certainly not in the near future. So today's topic, or for today, I would like to tell you about those weighted KLRW algebras. I'm not going to tell you all about weighted KLRW algebras. It's called weighted KLRW algebras, which means I'm going to kind of present my favorite parts of it. So all of this is recent joint work. I shouldn't call it recent. I'll explain in a second. With Endo. So it's really not recent. So we started this project a long time ago, so 6 years. And it was finally done, and then we realized it actually generalizes. So we put out a second paper, which is kind of useless in the sense that everything should have been in one paper. But anyway, that's just how it worked. Anyway, so there will be some combinatorics of diagrams involved. You can already see a spoiler here on my first slide. And there will be some funny notion, actually, kind of a really nice one. Comes up in those definitions of those weighted KLRW algebras. So about distance. So it's a diagram calculus, like Bauer algebras or whatever. Call some of them. But now the distance kind of matters. It kind of matters how it's embedded immersed, how it is presented in the plane. It's kind of a really fun story, and you really play along with this distance. That really helps you a lot. So it kind of makes the algebras in the end much easier. Also, the definition is much harder than some of the algebras I'm going to tell you today about, or kind of recall what they are. Okay, so kind of the idea, or where are we? Well, here's my little picture. I said here many people who worked on KLR algebras and stuff, of course, including my host, but other people I've seen in the audience as well. So Chris Bowman, for example, name will show up several times here. But KLR algebras and friends, they really at this heart of categorical representation theory. They're relatively new objects for in mathematics, if you want. Also, they have been around for longer, but kind of the date here I picked was 2008, which is 14 years by now. So time flies. It's just horrible. But anyway, so they really lie at the heart of many topics in modern representation theory. Even in low-dimensional topology. So at one point, for example, I wrote down a paper where KLR algebras are used to construct Covalent homologies. So this is how low-dimensional topology enters. Categorical representation theory is kind of where they were born. So they were born because they were categorifying certain irreducible representations of an associated Lie algebra. And kind of why a lot of people like it is this. It's kind of graded representation theory. It's this idea that actually classical representation theory is enriched in a more nice setup, in the graded setup, and you can play around with the gradings, like whatever. Simples are self-dual with respect to the grading that tells you a little bit more information about their dimensions, because now you have graded dimensions and so on. But much more is going on here. And there are several algebras. They all look kind of the same. And I'm kind of trying to recall or explain them in one setup. So they're also various algebras like quiver Schur algebras or Cherednik algebras, and they all fit in the same story. The real problem is, well, if you believe that my picture here, my main picture here in the middle, is actually an appropriate representation of what's going on, then it's probably a very complicated algebra we are talking about here. Okay, algebras are not easy. I still remember when I first saw the definition, which I'm not going to recall, by the way. It just looks like it's an algebra by generators and relations, and it just looks a little bit scary. It's not very easy. Those guys are not really easy. They're just really complicated. So so how can you approach kind of studying them? Whatever you want to write down simple representations, you want to write down their dimensions, something like that. And this weighted KLRW algebras, they're a really cool trick, actually, to study all of them at once. And making the definition even more complicated, so it will be a little bit of a trip. But in the end, there's a huge upshot, because those algebras actually tend to be easier than the KLR algebras. So, for example, you can much easier work out kind of combinatorics of cellular structures and so on. It's much easier in this setup. Same for Schur algebras and Cherednik algebras. In some sense, if you know KLR algebras, then those weighted KLR algebras are more like quasi-hereditary covers. They're not quasi-hereditary in general, but they are closer to a quasi-hereditary cover, if you want. Anyway, I'm not assuming that you actually know what those are, because they will turn up as a special case of construction, which take some time to record it. or to present it here. Okay, it's kind of the setup. So this slide should convince you, I hope, if you're not convinced already, that what I'm going to talk about is not just fun combinatorics, but it has some meaning to someone somewhere, maybe at least, who knows. So kind of the main idea, this is kind of the underlying flavor here of my talk, is that sometimes actually it makes sense to study a more complicated algebra to say something about smaller and easier algebras. Really, the picture I have in mind is, and then you can kind of interpolate between them. So we have two, well, reasonably easy algebras. So this is Z mod 2. This is just an incarnation of the group ring of Z mod 2. So this is Z mod 2. And the other one is not semi-simple, the dual numbers. And they kind of both appear as a specialization in this case of a bigger algebra, which looks more complicated, but it actually is more easy. It's actually easier. You kind of, instead of having two roots with a 0 or two roots which are plus and minus 1, respectively for the left hand and the right hand side, you just kind of throw in arbitrary parameters, or not arbitrary, you just throw in parameters and you get a different algebra, which looks more complicated, as I said. It just has a more complicated expression, but actually is easier to study. And I call this interpolating algebra. And the weighted KLRW algebra will play exactly that role of the big one here in this blue little box upstairs. And the KLR algebra, let's say, is this one, and the whatever quiver Schur algebra is this one, something like that. So that's how I would like you to think in the end about the KLRW algebra. And if you really play this game, that sometimes actually it's, as I said, much easier to work with the big algebra. So for example, if you would give this problem here, okay, those algebras are pretty simple, but you can think of more complicated algebras. Sometimes it makes more sense to make them more complicated, and a machine can, for example, work on a basis for you, because you have an extra parameter, an extra grading to play around with or whatever. And that's exactly what I'm trying to do in planar geometry, because that's kind of where the interpolation comes into the game. So how can I play this game of defining interpolating algebra, not in terms of algebra, but in terms of planar geometry? And it's kind of really, really nice. The upshot, takeaway message is that we get one algebra that kind of interpolates between those various algebras that turn up in, I just call it categorical representation theory, but modern representation theory, graded representation theory, the topic of this talk, whatever you want to call it, doesn't really matter. So kind of nice algebras that turn up in more modern parts of mathematics, in categorical, whatever, in categorical representation theory, whatever you want to call it. Really, so in the end, this is my main player, and these are the kind of the already complicated algebras. But as I said, the situation is of course much more complicated as this picture that I have in mind here. So KLR algebras is more complicated than dual numbers, right? So just to keep that in mind. Okay, before we get going, I want to get us all on the same page. So I start a little bit with string diagram combinatorics, and a huge flaw that will appear in string diagram combinatorics, which we then fix when we are going to the weighted KLRW algebras. So here's my string diagrams, my baby case. Of course, they describe the symmetric group in 8 strands, if I haven't miscalculated, I hope. So you should think of having 8 numbers at the bottom, 1, 2, up to 8. And they end up somewhere on the top. So 1 goes to 2, 1 goes to 2, 2 goes to 4. So this was a 2. That's correct. 4 goes to 3, and 3 goes to 1. So it's this picture, and so on, right? So this is, I hope I got it correct. 5 goes to 8, and so on. 7, so 5, 6, 7. 6 goes to 5. So 7 goes to 6, and 8 goes to 7. And here's another one. You can now check, or later when you can check later if I will send the slides to Liron. You can check later whether I messed up, which is very likely anyway. But kind of this is just kind of reinvented the symmetric group. It's kind of the point here. We're just playing with those funny diagrams. And you might argue that this is a cool way of thinking about the symmetric group. Some people might say that's a kind of silly way of thinking about the symmetric group, because you can just write it down in terms of your permutations, or your transpositions, or in terms of Cox's representation, or whatever. kind of the point of those KLRW algebras, these weighted ones, will be that I'm kind of copying this approach. Of course, it will be more complicated, but I actually don't know any good way of writing it down in other terms, right? So here I could write it down in terms of string, I have string diagrams. I could have written it down in terms of more classical algebraic notions. I don't have any good way of doing that for the weighted KLRW algebras. So if somebody knows, I would be interested, but I kind of doubt that there is some, because as you will see, there's some built-in geometry. Anyway, so this is kind of nice, and you can play around with your diagrams. You can just compose them, hoping that I haven't messed up. And if it ever plays a role in my talk, I'm actually not convinced anymore. But then I will fix my conventions now. So this is, I will multiply the blue box with the red box, and the red box comes on top. The blue box comes on the bottom. And whatever, you straighten out your diagram. And I hope, again, I haven't messed up. It should actually work automatically, so I have kind of a little program that does that, but you never know. I hope I haven't messed up, then you can just simplify it to the picture on the right. So it's kind of nice, right? You can diagram algebras, you can play around with them. We've just rediscovered the symmetric group S8, and of course, Sn in general. Just take 15 strands, 20 strands, whatever you want. And it's pretty nice and pretty well known, and everything kind of works out in a very nice way. Right? You can write down usual generators and relations. Also, you don't really need to do that, but you could formulate it in terms of, let's say, certain type of cobordism diagrams. But anyway, so it's kind of very nice setup. The identity, I should have said that, is this little boring diagram here on top, where you just do nothing. Well, makes sense, right? 1 goes to 1, 2 goes to 2, and so on. And generators and relations, it's just what you're going to write down. The Reidemeister moves will play a role, so that's why I decided in this little recap on what diagram algebras are to recall the symmetric group, because, well, the Reidemeister moves will play a role for the later algebras. So it's kind of the baby case of string diagrams, and people have generalized it in many, many ways. So string diagram around for donkey's years, of course. I'm not quite sure who drew first string diagrams, but they are old handwritten notes of Gauss from the 1800s, and Gauss writes down string diagrams. So more precisely braid diagrams. It's kind of the same, but they're at least 200 years old. So it's quite a lot. It's quite a lot. Still, most people would still call them kind of a non-standard way of doing mathematics. But anyway, this is kind of the point I want to generalize. But there's a huge flaw. So let's have a look. So let's go back. Okay, we have string diagrams. They kind of live in the plane, fine. They intersect, good. I don't really care. So they immerse, not planar, but that's fine. They still live in the plane. You can kind of nicely contract them, stack them together, and whatever. Everything kind of nicely comes into the game. Like associativity is completely obvious in this picture and so on. Very good. So this is kind of the bait. So everything is kind of obviously built into the diagram calculus. You can read off properties of symmetric groups if you want. I haven't shown any of this in the slide, but you can think about traces, for example, if you close the diagram and so on. So it's pretty nice. But actually, it's not really. It's actually not really true what I'm saying. It's just a lie. You know, I'm not really using any planar geometry. I'm just drawing diagrams. The only thing I did is, honestly, I just replaced the algebraic symbols with different symbols and just used the same rules as before. Right? They're just algebra written differently in some sense. Very effectively, I'm not doubting that, but it's just kind of a little bit of cheating. You just do exactly the same thing, you just draw different diagrams. A little bit of cheating. So that's kind of the catch of this whole setup. And the idea which I would like to contribute to Webster, and I've never seen it anywhere else, which is kind of fun, is that you can actually define an algebra which really uses planar geometry. The geometry of the plane. And it's not just a diagram algebra written diagrammatically because you want to. It really uses the geometry of the plane. And these algebras are called weighted KLRW algebras for a reason I'm going to explain in a second. So the weighted is a little bit mysterious right now. I'm going to explain that. KLRW is, I hope, reasonably clear. So KLR is the usual, I hope I had the name somewhere in the beginning, the usual KLR, so Covenant of Lord over K, and the W is for Webster, so KLRW algebras. question is where the weighted comes from. And they're really just, as you will see, they're really almost the same diagrammatics, but with some extra nice, spiced up, a little bit nicer, really using the geometry of the plane. And this is just a funny thought I had when I was thinking about what to put on the slide. Actually, I've never seen anywhere else this idea applied, and I'm pretty sure that it actually should work for other algebras. So most diagram algebras you ever see in your life, they're really not honest topological objects. They're just algebra written differently. And I really wonder, so kind of, if you want to think about it a little bit, that this approach by Webster kind of makes more sense for other types of algebras. I just applied today for the KLR algebras. Okay, so that's kind of the setup, and I will use string diagrams to construct those interpolating algebras. And then kind of in this setup, everything becomes easier. Okay, that's what you should keep in mind. And now we're going to dive into the combinatorics, which is, well, combinatorics. So we'll take our time to explore it and kind of keep in mind what we want to do. We want to construct those algebras and kind of interpolate between all the others in an honest topological way, or maybe in a planar geometrical way, whatever you want to call it. You can decide later for yourself how you would like to call it. And this is really the setup. Okay. So it will be a little bit of a mouthful. As I said, it will, I think 5 times by now. I know I sound like a broken record, but it's important kind of to emphasize that the definition looks really, really complicated, but it actually is much better than kind of everything else you could do with scalar algebras as far as I know. So stay with me here. It will take a while. Okay, so I would like to draw string diagrams, and I call them weighted string diagrams. Fine. They really look exactly, I mean, I just copied the diagram from before, so let's have a look. This is just really just this one copied. I was just too lazy, right? Same diagram. I just decided to color it, so everything here now comes in 3 types. So there's 3 types of strings, and for reasons, I don't know, they're just called, we could call them string type A, string type B, string type C if you want, but usually they're denoted by a solid string, which is bluish in my notation, a ghost string. I don't know where the name comes from, by the way, it's just a strange name, but anyway, it's kind of a ghost. You will see in a second why the name kind of makes sense, but anyway, there's a ghost string, which is this grayish and dashed notation, and there's a red string, which is, well, red, I guess, a little bit thicker and reddish. Okay, so we have 3 types of strings. Kind of the difference to the usual setup in string diagrams or in symmetric group diagrams is that now everything is colored with either solid, ghost, or red, or if you really like to think in terms of colors, blue, this grayish color, I'm not quite sure what it is, and red. Okay, so you have types of strings. Fine. But otherwise, it's still kind of the same combinatorics, and of course you can still stack diagrams and so on. So that's still fine. There's also another ingredient here. So strings can carry dots. And there's only one rule how this works. The only strings that can't carry dots are red strings. Okay? So red strings are never carry dots. So this one never has a dot. Never has a dot. And otherwise you can put your dots everywhere, and I'm kind of using implicitly here that you have drawn everything in a generic way, so dots shouldn't lie on stupid intersections, there shouldn't be any triple points and so on. Kind of a really nice picture. And they just move freely around their strand. They can pass through other dots, that doesn't matter, but they can't pass through crossings a priori. There will be a relation that enables you to pass this dot through this crossing, but a priori it doesn't. So the diagram's up to isotopies, and isotopies in this case involves moving dots along the line, but not passing over other strands. Okay, just move it. And it's kind of a fun setup. So there's another label which I need to explain in a second, or which I need to explain in a second. Yeah. So the point will be that the red strings, they kind of anchor everything. I'm kind of explaining later where they come from. And you should think of them, if you know this terminology, as being a level. So there will be a certain number of them, and this number will be the level of the calculus. So you can give everything a little bit extra flavor. There could be 2 others here, and 1 here, and 1 here, whatever. Then it would be So this is not really a red string. Let me get rid of the red string. Then it would be of level 1, 2, 3, 4, 5. Great. So the number of red strings. This is what people call the level. I tell you this later where they actually appear. But for now, it's just the main players are actually not the red strings. They're kind of anchoring the diagram. That's what they need to do, because we kind of want to play this planar geometry game. And well, they should be somewhere. So think of it as a strip in R2. Then I kind of want to know where I am on R2. R2 is a little bit too big, or maybe this is just R cross. So R is the most important one here. R cross and whatever 0, 1. And I kind of want to know where I am in R and kind of use the red strings to anchor everything. They bound me a region, and actually everything is really happening in that region bounded by those strings. And kind of the combinatorics comes from all the other strings. Yeah, so they are labeled not just by colors, but also by certain funny numbers, which I'm going to explain in a second. So you have strings in 3 types, and they are labeled by numbers. And for some reasons, I decided at one point that their labels should go over ghosts and under written solid strings, which is just because sometimes the ghost is very close to the solid string, and then you can't read the labels anymore, so I decided to put one up. That's just convention. Point is, they are labels, and where you put them is just convention. Okay, string diagrams. That was probably too quick anyway, but let me just repeat it. So symmetric group diagrams. These are just symmetric group diagrams. You have 3 points of extra information. You put dots. You have certain types of strings, red, gray, and blue, and they come with certain labels. Fine. And kind of everything will depend on them. Kind of the relations they will satisfy. In the planar symmetric group case, you just have those Reidemeister relations. And here it kind of will depend in the end on the involved combinatorics of the strings. Okay, weighted string diagrams. And where does actually the weighting come from? This we try to explain a little bit of the input without fixing too much. So assume that you have a given quiver, anything. So quiver, any quiver you can imagine, with some vertices that are denoted by I. For some reasons, so in this field they're usually denoted by I, not quite sure why, but E are the edges, that makes more sense. So vertices I, edges E. For example, you can think of those quivers, Doped quivers of a certain type. If you like this one, maybe the affine type A, the circle. And the labels for the strings are just the vertices of the circle. So number your vertices in some way, whatever, 1, 2, 3, 4, 5 up to E-1 or something, and the labels of the strings are just the vertices. And then the relations depend on the quiver. So for example, you would get a relation like this, with kind of a flawed Reidemeister 2 relation. So whenever you have an edge between I and J, well, let's say to take this pair, and secretly there's an orientation which I haven't forgot to draw. So there's some orientation. Let's say it's pointing in this direction. So I would be -1 here, and J would be 0, I guess. And then you have this type of relation. So you kind of have a Reidemeister 2 move. You kind of can play this game. So here's my ghost string, here's my solid string, and you kind of can play it, can pull it straight. But not quite. You get this error term, and the error term in this case is the dot placement. This symmetric, almost symmetric up to sign dot placement. You put a dot on the ghost string, and you put a dot on the solid string up to a sign which I never remember in which direction it goes, but the sign is also important. So it's kind of a Reidemeister 2 move, and this Reidemeister 2 move is one of the most important moves, one of the most important relations in this algebra. And you have other types of relations that they're just Reidemeister moves a little bit flawed. Like we have Reidemeister 3 move depending on the input of the quiver. And it looks like a Reidemeister 3 in most cases, but if you have an edge, it's a flawed Reidemeister 3. It's kind of a deformed symmetric group calculus if you want. And they really depend on the edge. I would like to highlight that I'm always confused about that myself. It doesn't really depend on the vertices, but it really depends on the edges. So you could imagine that you have one edge with a lot of vertices going out. Then each edge gives you a relation, and not the vertex has a relation itself. So each edge will give you a relation. But anyway, it plays some role for some types when you have kind of crazy edges going in all directions. But anyway. Okay, so I'm decorating my diagrams basically with the quiver. And the quiver is, of course, where Lie theory comes in. So a priori, I can take any quiver, but the main important ones, kind of the combinatorics is always the nicest or the most complicated one, whatever you want, for the classical or affine Dugit quivers, like, well, the AC that I've put here on the slide. You could do type E or whatever you prefer. Okay, so beefed up symmetric group diagram. So far, nothing related to planar geometry. So I was lying in the past 20 minutes. There is no planar geometry. Of course there is. Just kidding. But this is kind of the combinatorial setup. So this is what links it to Lie theory, right? So relations that depend on edges of a quiver. That's how you can formulate it. Up to let's go to planar geometry here, which is the first time I actually use the number pi in a talk. So it's kind of fun. I realized that and I put this little box here. The first time I use the number pi in the talk. So the point is, and this is kind of funny, this is something you probably haven't seen before, because as I said, this is an idea due to Webster, I haven't seen it anywhere else. But in this algebra, it's not just the combinatorial relations depending on certain types of strings or depending on a quiver will change the type of the algebra, but also how the strings are placed on the real line. It really makes a huge difference. I will make a more formal statement later on. So you could think of those, well, there's an extra choice, namely an extra choice involved where you place your strings. I just tried to, I just made one choice here. Obviously I wanted to include pi, but you can choose whatever you want. So the red string anchors my diagram. I just put it at place 0, right? This is a real line, and I just say, okay, it sits in the origin. And everything else is kind of anchored around the 0. And I hope I haven't messed up my calculations, and pi is really roughly around here. So this is spaced at pi, this is spaced at 5, so pi is roughly 3, that works anyway, and some square roots just put in, because any real number, you can just put them in any real number. Doesn't need to be an integer, doesn't need to be whatever, it's just any real number. Okay, so this is kind of fun. So you have more input than usual. You also space your strings in place your strings in space, not space your strings in place. Space your strings in, let me try again. Place your strings in space, depending on the choice this guy is called a loading, depending on the choice of positions for the solid strings. Okay, so far not very exciting. You can still argue, I could just pull this string here a little bit closer by using some kind of straight line diagram. It's kind of the same anyway. So why do you bother actually to really carry the positions around? Right now it doesn't really matter, but there's a fun trick to actually make it work. And this is where those ghosts come in, okay? So the ghosts are determined as follows. Say it again. I only choose positions for my solid strings. So the red strings, ignore them, they just anchor everything, fine. I should choose positions for my solid strings, and I kind of need to tell you where the ghost strings go, and that's where the weighting comes in. So actually I was lying, lightly lying. I'm not just choosing a quiver, I choose a weighted quiver in the sense of graph theory, and it just means I choose a real number, 1, whatever, 2, pi for each edge, and it's called a weighting. So each edge gets an associated number as well, and that's now plays a role. So here in my example, I should have chosen pi, I realize that now. But anyway, it's -1, 1, and 0.1. So 0.1 standing for some small epsilon value. And the way this determines now the ghost is as follows. So whenever you have let's take this example here. So whenever you have an I string somewhere, so here in the I string, it's somewhere, it's placed somewhere at position A, whatever. And there's a weighting 1, I would place the ghost string at position A plus 1. So A plus the weighting. So here it would be a plus 0.1 and so on. And the ghost string kind of is a ghost, maybe that's where the name comes from the original string. It just mimics exactly the movement. So let me try to draw another diagram. So if I would have a solid string like this, it's labeled I, and I'm also in this setup here, then roughly 1 unit to the left, which might be here, there will be a ghost string mimicking its movements. I can do that better. Give me a second. I can do this much better. I just mimics its movements. Here you go. And just make it gray. I can't dash it. I'm not sure how this works here, but it just mimics its movements, and it shifted certain units to the side, and the units are given by the weighting of the quiver. Or let me move those pictures aside so that you can read what I've actually written. So what we do here, yeah.
Are you going to use different numbers, or are you going to will your graphs always have the same label on every edge?
Absolutely not. I can put everything I want. 1, 2, pi, your favorite number.
So you will space strands out differently according to residue?
I will space according to the weighting. Yes, that's right.
Yeah, okay. Yeah, but like if a residue is 1 and 2, they'll be further apart, or?
Oh, so what Chris calls a residue is the color of the vertex, the name for the vertex. But a priori, that doesn't have anything to do with what kind of weighting I choose for the edge. Everything works for the edge. Okay. So if you look at string I, you really need to look at the weighting I've put on the edge to really determine how far it is away.
Okay.
Make sense?
And the ghost edge, it doesn't care about the target of the edge in the quiver. It only cares about the source.
Almost. If there's kind of a funny convention to make it more symmetric. If there's a negative label, then the ghost will be the ghost of the target, not of the source. This gives it extra symmetry on the quiver. But I kind of want to ignore this case. So if I'm going to ignore negative numbers, then you're right, and I don't care about the target, I only care about the source. Okay? Any other questions? I know this is a lot of combinatorics. Good. So we have kind of a lot of data here, right? You place your solid string somewhere at pi if you want. Completely independent, complete free choice. You can choose freely. You place your ghost strings according to a weighting of the quiver. Again, complete freedom. Just whatever works. And well, the KLRW algebra is an algebra then defined on all those combinatorics. With an associated graph, it gives you the relations. You have those choices of positioning, which kind of place the string in space. And everything depends on those choices. And I will have a nice example, I hope, at one point, if I haven't kicked it out, otherwise I just do it live anyway. So this KLRW algebra depends on the choices of those endpoints. It's really the bigger algebra. Kind of in the KLR setup, you don't know what those, you don't have choices of endpoints. In this bigger algebra, you can now vary all of these endpoints and ghosts and everything. So you kind of get all the other algebras. As I said, I'm going to make a more precise statement in about, let's say, 10 minutes or so. Bear with me with my combinatorics here. Okay. That's what I just explained. So, and the question here was, according to this asymmetric choice, preferring source over target. Let's ignore that for now. Let's just say you always prefer source over target, and you shift everything to the right. But I shift everything always to the right. So let's try to understand this example here. Maybe this makes more sense. And I'm now contradicting myself with it because I decided to put in a negative number anyway. Okay, let me start again. So we have a vertex I, and it has 3 outgoing edges, and there is some epsilon. So epsilon is just a really tiny shift. 1 minus 1. So coming back to Chris's question, you can put anything you want, right? Okay, so let's see whether we understand. I is connected to j, and the number is positive. So I should have a ghost that's 1 unit apart. So here you go. Very good. I is connected to L. I ignore the source, right? The target. I is connected to L, and epsilon is very, very small, so there should be some ghost that is very, very close, and indeed there is. I is connected to K, but the name number is negative, so K should have a ghost roughly 1 unit shifted to the right. It's kind of this funny convention that gives it a little bit more symmetry. And now imagine you have a huge quiver, a lot of edges, a lot of shifts everywhere, and you get lots of strings and lots of ghosts. Looks very complicated, this algebra, as I said. Kind of a nice way of thinking about it. Here's another example. So you can have 2 outgoing edges, you can get 2 ghosts, absolutely no problem. One of them being 0.5, whatever I've chosen here, and one of them maybe being 1.25 away, something like that. And it should mimic the movement. So whatever the one string does, the other one does the same. Makes some sense, I hope. And then you get this funny where does the geometry comes in? Well, the geometry comes in as follows. So let's say you're looking at this picture. It makes it kind of really nice and really fun. You're looking at this picture and you think, string I and j, they look very close to one another. So I could pull them arbitrarily close to one another, such that I can apply some relation like whatever. There's a relation that looks a little bit like this, whatever. Maybe I can apply it because I can pull the strings close to one another. Actually, you can't, because the ghost strings are separated. Because the ghosts always mimic the movement of the parent strings, you just can't pull them close to one another. The ghosts are separated, which gives this algebra this funny flavor that now distances really matter, because now it really matters whether I've put the K string in between or whether I've put it here or whatever. Also, I can't locally see it. It still matters where it's placed in this diagram. Right? If I accidentally, of course, in this I've constructed it, I hit exactly the spot between I and j, then the diagram is stuck actually. It's kind of so I and j are not close. They're far away from one another in some sense. You can't pull the strings arbitrarily close. And this prevents the whole setup to be scalable. So usually in diagram calculus, it doesn't really matter where you put your endpoints because you just scale the diagrams. Here you just can't, because there's this nice interplay between the various numbers involved. You just can't really scale your diagrams in any too artificial sense or a too arbitrary sense. Right? So this really is a difference between the diagrams and the usual diagrams. So those diagrams and the usual diagrams. That's really just what it is. And the A and B are kind of the positions of the ghosts. So we choose positions and ghosts now. And for certain positions you get certain algebras, and for certain other positions you get certain other algebras. It's kind of the whole point. And this is kind of I don't have really time to explain how this works, but this is kind of how you should think about it. So if you like any of those algebras, so KLRW would appear, for example, for epsilon ghost shifts. You can vary that a little bit. So in Chris's paper, he does something slightly different, which still works. So they might show up for different shifts. So the same algebra might show up for different positions and shifts. But what always works is the following. So you get a semi-simple algebra if the ghosts are very far away. Right? So here's your solid diagrams, and the ghosts are very far away. Then there is no real interaction between them, and you get a semi-simple algebra actually. So I call it huge ghost shifts, whatever. And the KLR itself is kind of the opposite. So when ghosts are very close, epsilon close to the parent string, then you get a KLR, and this works at any time. There will be ways to put in Schur algebras for certain choices, which I'm not going to recall. There will be ways to put in diagrammatic Cherednik algebras, like in the paper of Chris. Chris kind of asked this question because in Chris' setup you would have ghost shifts that are all one, but you can really vary them when you get many different algebras. So I just unnamed algebras the rest. For any choice, you get some algebra. So this big interpolating algebra. Okay. So let me nail down choices a little bit, or just make it a little bit nicer. So here comes a really cool picture how to think about those weighted KLRW algebras. Even if the combinatorics was a little bit too quick, I mean, it's complicated combinatorics. Don't worry, the only thing you need to remember is there's some distance involved, and kind of the distance determines the picture. So coming back to my example of this algebra, which is of course way too simple, but we'll see the more general picture in a second. It kind of works like this. So it looks like you have an arbitrary two-parameter family of choices. You can choose here two complex numbers for A and B, right? But it's not really the case. There will be some Morita equivalence classes involved. Same will happen for the KLR algebra or for this weighted KLRW algebra. So here it's pretty simple. So in this case, there are only two Morita, or actually isomorphism classes of algebras. The green background, which is kind of everything, and the red line. So whenever A is equal to B, so you have two equal roots, it's actually isomorphic to the dual numbers, the non-semisimple one. As soon as A is not equal to B, you have two different roots. You can play some Chinese remainder theorem game to see that this is actually the algebra from before, so the group ring of C-mod 2. Right, so it's only two different cases, actually. So even though it looks like there should be infinitely many two-parameter family, there are only two. And there's a nice, really nice picture for the KLR algebras as well, which is kind of a lot of fun to think about, and I'm going to explain it now. Just remember those KLR algebras depend on various involved choices of positions. So kind of the point is here there are hyperplanes. It's really like a hyperplane picture now. It's got a very nice it's a high-dimensional one, and I'm just using a very, very small example that I can draw. I'm really, really bad at illustrating anything beyond dimension 2. I'm very sorry, but let's stick with the picture. I think it will be clear in the end. So we get hyperplanes, and the hyperplanes are given by the equations when the strings would overlap. So I fixed here my position rho, and x is the position of the, so here I'm kind of vary the position of the red string, and here I vary the position of the solid string, and I keep kind of the ghost fixed to make it not too high dimensional. So the ghost is always, so this shift is always the same. And I kind of vary my strings. And here, when x is big compared to rho, maybe I messed it up. No, let's have a look. So here's a hyperplane. So there's a hyperplane where the solid and the red string will overlap. So at one point, if you move your diagrams, you kind of move the endpoints of the strings, the solid and the ghost string will overlap. And that will be this hyperplane, given by when the coordinates overlap. So you can write down an equation in coordinates, and it will give you a hyperplane. And here would be the same, so I'm pulling my red string even further to the side when the ghost string and the red string overlap. That will happen at one point, a little bit later maybe. And you can see here, so A is kind of my first setup here, then I pull the red string a little bit towards the middle, I kind of jump in the next region, and I pull the red string a little bit further, and I jump in the northwest region here. So for each region you have those certain diagrams depending on how far your strings are. So where your strings are in relation to one another, and you have hyperplanes given by strings collide in a huge dimensional space depending on how many strings you have. Okay, so this is kind of a nice kind of picture, and the main theorem that you can prove is, so you have some hyperplane picture like this, get arbitrary complicated. Think of whatever I said, a 500 dimensional space with some hyperplanes. And within one alcove, within one connected component, you can actually show that you have a Morita equivalence class of those algebras. Okay? So each one of them corresponds to a Morita equivalence class of those algebras. And at one point, you will see a direct Cherednik algebra. There will be one corresponding to a KL algebra, and so on. It's kind of, that's the correct picture, I think, how to think about those algebras. So in the end, you don't really have infinitely many parameters or parameter families to play around with, but there will be certain regions given by those equations where strings overlap, where you get your favorite algebra, basically. One of them. So one of those alcoves will be given by KLR algebras, one of those alcoves will be given by semisimple algebras, and so on. It's kind of a nice generalization of exactly this picture. Sorry, but now. Kind of lots of hyperplanes, high dimensional equation, high dimensional space, lots of algebras floating around. and each alcove, each connected component, gives you Morita equivalence classes, those algebras, and you can actually write down.
Can I ask a question, Daniel?
Absolutely.
So, just because of this picture you have on screen, it's made me think about this. You said earlier, was it semisimple comes about if the ghost distances are massive,
yes,
and KLR if they're tiny?
Absolutely.
But KLR algebras can be semisimple. So how do I think of a semisimple KLR algebra in this setting?
So scalar algebras can be semi-simple, absolutely. What I'm precisely saying is whenever the ghost shifts are huge, you're guaranteed to get a semi-simple algebra. The other algebras could also be semi-simple.
Okay, all right.
Makes more sense?
Thanks. Yep, thank you.
Great. Yeah, sorry. But yeah, okay. Yes. So now I recall what I wanted to say. So in this picture, if you have seen this before, you can actually play a funny game, which I don't have time to go into details. But as soon as you have hyperplanes, you should think about translation factors that kind of jump from one hyperplane to the other. And you can actually play this game of translation factors here. So you get kind of translation factors between those various categories associated to those algebras. It's kind of a nice setup. And the translation.
So here, Daniel, have you fixed a quiver, but you're playing around with the loading on the quiver, or is it?
Gamma is fixed. Yeah, that's right. There's a way to vary gamma as well, but I'm not explaining that. That's right. I'm only playing around with the positions. I'm fixing the discrete properties. Fixing the. Thank you very much. Yes. So we have this theory of translation factors. So those translation factors, coming back to Chris's question, they only really relate to KLR algebra of a certain type to a quiver Schur algebra of the same type. Right? So they're not jumping between types. But it's still quite kind of a nice setup. Okay. Yeah, I would like to tell you a bit more about how distance can be really, really useful. So by kind of explaining how to construct the cellular basis for those algebras. Again, the type is fixed. This is a little tricky, so I think it works in kind of any type, but we haven't done that yet. So let's just ignore that we have done that yet, and I will zoom in into a specific type in a second. But my story is actually that distance, is it right? So the distance matters. Mind the distance was, I think, mind the distance between the train and the platform was, I think, the subtitle of my talk. So there are many other ways to play around with the distance, which makes those algebras much nicer. So for example, the cyclotomic quotients, I'm not going too much into details about cyclotomic quotients here, but usually the cyclotomic relations are a little bit ugly, they're non-local, and here it's pretty nice, and taking those quotients is usually very, very simple. So for the experts, in the end, what we will do is, or what we did in this paper, the joint work with Andrew, we kind of wrote down a nice cellular basis for the affine case, so where the algebra is infinite dimensional, and the cyclotomic quotient comes for free because it's so simple as defined here on the slide. So it works as follows. So you have some red strings somewhere, they kind of bound your diagram, and I would like to think about the red strings as giving me kind of a little box somewhere, and there will be some more red strings, God knows. Kind of a leftmost red string and a rightmost red string that bound my regions. And cyclotomic means I'm staying in this region, basically. And if I can move out of this region, it's kind of killed in the cyclotomic quotient. It works as follows. So whenever you have a string, you kill all diagrams as follows. So whenever you have a string that pulls freely, let's say to the right, there's some choice involved. You can just pull it without anything stopping it. As the red strings stay in a bounded region, and you just pull the string, then you just kill it, and that's the cyclotomic quotient. So in this example, and they call it unsteady. So Ben Webster calls it unsteady. Not quite sure why, but it really is, it pulls freely. Okay. So here, because the ghost will mimic its parent, I can just pull the string. It will just go all the way as far as I want to, and the ghost, which I'm not going to do dashed anymore, but anyway, it just goes along, and I just pull it and pull it and pull it and pull it. Okay. So it goes pulls freely as far as I want to the right. You would kill such a diagram in the cyclotomic quotient. And you don't you can't pull this string freely because I'm saying that the red string stays in the bounded region. It's just blocked. You can't do it. And this really is a kind of a geometric description of those cyclotomic motions. It's just really, really simple to work with. If you define everything appropriately, you can easily see what will die in the cyclotomic motion. And the cellular bases, they kind of correspond to kind of minimal regions in the setup of there's a bounding box, and you kind of make that as small as possible. And there are more properties that I don't have. Actually, I don't have time. I'm already running out of time. I only have roughly like 8 minutes left. They're all related to this how you place strings in space, which is such an amazing idea. I still want to promote it again. There should be some kind of general theory of those algebras, not just weighted KLRW algebras. And it's a really cool idea. Okay, so let me try to explain how we construct bases for those algebras, which is much simpler than you actually would think it is. It's just surprisingly simple. Okay, yeah, so I have 8 minutes to 7 minutes. I'm waffling too much, I'm sorry. I have 7 minutes to explain the whole setup, and yeah, let's see how it works. So I would like to think of two types of bases. Okay, so I would like to think of types of standard bases, which you might have seen in different setups. So there will be standard bases. Usually the terminology standard is just used for everything anyway. I'm going to explain in a second what I mean by standard. And there will be cellular bases, put in quotation marks because you kind of need to be a little bit flexible what you mean by cellular here. So if you ask me later, I'm going to elaborate a little bit. But anyway, there will be some cellular bases. And kind of the point here is that the standard bases are kind of biased to a side. So what you usually do is you have some diagrams, you have some dots on diagrams, whatever. And you kind of have a relation to pull dots. So you put all crossings at the top, and you put all dots at the bottom, and you do that in a reasonably controlled way, and you get a standard basis. Crossings at the top, dots at the bottom. And for a cellular algebra, you would like to do that in a more symmetric way. So you would like to have a top diagram and a bottom diagram, which I call T and S. Like top and bottom, fantastic notation. So my top diagram and my bottom diagram. And you have the middle diagram, which are still kind of dots, but they're now sandwiched between whatever, something like that. That's a horrible that's a horrible drawing. But anyway, so you have a permutation diagram at the top, and you have a permutation diagram at the bottom. Maybe I should have referred to this picture which I stole. So just straight lines in the middle with some dots and some permutations, top, bottom. And these are also bases for those algebras. And these are this is kind of the idea of a cellular basis, and this is the idea of a standard basis. So a standard basis is kind of standard basis is something a computer would write down, because a computer would just order them, gives them a certain degree, put certain elements to the front, put certain elements to the back. That's a standard basis. And a cellular basis is a little bit more sophisticated, and it gives you more symmetry. That's why I want to do it. But you kind of sandwich, in my picture, it's this way, you sandwich a certain nice diagram in the middle. And in this setup, it's really a permutation at the top, permutation at the bottom, and usually you want to put an idempotent in the middle, and the idempotent should correspond to the simple module you have in mind. But it turns out that in this setup, you would need to put dots as well. So you get a dotted idempotent. Fine. In general, in type A, by the way, you don't. In type A, you just get an idempotent. But in general, you would get a dotted idempotent. Right? So standard basis kind of the point. A computer would write that down. So if you would feed KL algebra in a computer and ask for, do some Gröbner theory, some non-commutative Gröbner theory, you would get out the standard basis. Cellular bases are much more complicated. I don't know any good way to ask a computer to write down a cellular basis. It's just much more complicated. But they kind of give you a classification of simple modules among other properties. That's why I want to do this. And strictly speaking, I should kind of use the correct adjectives here. So in general, the KLR algebras are not cellular. I warn you, in general, they are not cellular. They will be affine cellular or sandwich cellular, depends a little bit on the setup. It's kind of a version of the same trick, a little bit more sophisticated. You need to be a bit more careful. Okay. So standard basis, what the computer gives you. Cellular basis, what you want, because you want to write down kind of the simple module. I'm not going to recall that. Just 3 minutes left. But anyway. And the point is, in this weighted KLRW setup, actually the way to construct cellular bases is always the same. It works for all types. And actually already appears in Chris's paper, but it's slightly differently formulated, I would think. But anyway, it just really works for all types, with some details differing, and with the precise form of cellularity also differing between the various types. So we only worked it out in certain types by now. Hopefully at one point there will be more, and they should work even more general. So I think it should actually work for any type, but future one. And I will trying to zoom in one of them in the last 3 minutes, because as I said, the combinatorics will be slightly different for them, and I decided to zoom in into type C, because actually type C is the easiest one. It's actually easier than type A in some sense. So let's actually do type C. So Chris did type A, a slightly different setup, as I said, and kind of Arikipak and the Leron kind of did the cellular stuff. Not quite, but they never wrote down the cellular basis, but kind of the same combinatorics that defines type C. Okay, I have 2 more minutes to go. I will take the 1 more minute because I started 1 minute late. I hope that's okay. And I'm going to explain it in this funny type, because actually it's pretty simple. So I just lied. I can't ask a machine to construct the cellular basis in general, but I can ask a machine to construct the cellular basis for the scalar types, just to prove that their cellular is a little bit more involved. And the code is just the best for type C, which is the flaw of the setup. Just you do type A, you're happy with type A, you do type C, you realize it's actually much easier than you thought. You write the code adjusted to type C, and the code is better in type C. That's just, I don't know, it's silly, but it's just what it is. So stay with me, I'm going to do type C. So type C is this diagram, and it works as follows. So we still want the same picture here, some diagram like this. I'm not going to go too much into details how to define the permutation. There's a tableau involved. As soon as you have a tableau involved, you just permute the entries that defines the permutation. So let me just focus on the middle, which is really the crucial ingredient. And it's kind of a really nice idea, which I shouldn't have said. I contribute this idea to Chris, so I can call it a nice idea. So a very nice idea how to construct those cellular bases. That was the middle part. Okay, so this is how the combinatorics works. I just put it on the slide. You have everything here is tableau combinatorics. You can make that more general by using root combinatorics or something. But for this type, it's nice tableau combinatorics. And this is how it works. You just put your tableau and you have a certain number, the residues, so the labels of the vertices go in the tableau like as follows: 0, 1, 2, 3, and 3 is E here in this case. Maybe it's actually, E is actually 4 in this case, because you have the stupid shift by E minus 1 here. Anyway, and you bounce back, so 0, 1, 2, 3, 2, 1, 0, 1, 2, 3, 2, 1, 0, 1, 2, 3, 2, 1, 0. So you always bounce back and forth, 0, 1, up to E or E minus 1, I never remember, and then you bounce back. And the trick is now you want to use the distance and this combinatoric to define for you a cellular basis where the top and the bottom part, they come for free, and you only kind of need to worry about the middle. And what you do is kind of a funny idea. You actually, well, I'm done. As you can see, I'm done. This says done here. So so it's really, really simple. You just do it in a minimal way. So you just read off your residues. Your sequence here, you just read like this. Actually, any way of reading would work if you're careful enough. So here I would read 0, 1, 2, 3, blah, 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 and so on. I just get this number, this vector of numbers. So each one corresponds to a string I would like to place, and I just place it as far to the right as possible without killing it. So, by the way, for the experts, the as far to the right as possible is now the cellular order. So the cellular order is kind of fun. It's just given by how far strings are to the right or to the left, depends a bit whether it's bigger or smaller. And each one of them, I just give you an example. And then you place the next one as far to the right as possible without pulling arbitrary far. Place the next one, without pulling arbitrary far. You place the next one. It's a greedy type algorithm. You define, in each step you define the as rightmost as possible, and in the end you kind of get a minimal or a maximal diagram. Depends a bit what you want to call it, minimal or maximal. Let me just, so all these examples are created by a machine, so it's very easy for a machine. A machine can just do it. Okay, so this is how it works. I just explained one of them. And this works in general, so don't worry too much about type C here. Somewhere I have a red string that anchors. I'm already 1 minute over time. I hope you forgive me. You have already a red string that anchors the diagram, and then you place the first string. So here, let's do this one. The first string is a 0. It goes to here. There's a slight epsilon involved, so put it epsilon far away from the red string, such that it is as far to the right as possible, but doesn't pull freely. Right? That's kind of the point. It has to go somewhere. Now my gray is really bad, so let me switch to black, and let me move the diagram a little bit more to the side. It has a ghost somewhere, and the ghost will stop the next string. So you put the next string here, and it has a ghost somewhere, and you could put the next string, and it has a ghost somewhere, and so on. And you will create those diagrams, which then depends on the sequence of entries that you see. Just place the string in kind of the minimal position, the maximal position to the right that doesn't pull freely. And that's it. And there's some dot placement and combinatorics involved. I can't explain because I'm 2 minutes over time. And I just want to wrap up. So KLRW algebras, you generalize KLR algebras and friends. Keep this hyperplane picture in mind. Have somewhere as a KLR algebra, somewhere as a different algebra, somewhere as another different algebra. There might be overlaps that's related to Leron's question. So this was just a kind of numeric picture. So semisimple and KLR might overlap, or KLR and quiver Schur might overlap. Kind of that's the overall setup. And this works because we have this built-in distance, and kind of most properties of those algebras are actually independent of the type. You can make them work for any type you want. The hyperplane picture works for any type. The cellular basis should work for any type. It's just not worked out. And almost all properties should be independent of the type. You always kind of use the distance to play your game. I said again, for example, the cellular order is just given by looking how far strings are to the right, which is an extremely simple description of the cellular order. And of course it's type independent. It doesn't really see the type. The type comes into the game for the cellular picture by the corresponding residue sequence that's given by the type. But the overall setup and the overall picture is actually really just the same. Okay, so much more complicated algebra, which in the end is much easier because you kind of can play this game of pushing strings from left to right, from right to left, and it really makes a difference. In usual diagram algebras, it just doesn't make any difference. Anyway, I'm 4 minutes over time, so thank you very much.